Everything is in motion. A leaf falling from a tree, a rocket launching into space, even you, just sitting there. But what's actually making things move? Well, today we're going to pull back the curtain on the invisible rules that run our entire world, the fundamentals of forces and motion.
So let me start with a question for you. What could a simple rubber band possibly have in common with a massive planet in orbit? It sounds a little crazy, I know, but the answer shows us that they're both playing by the exact same elegant set of rules. Let's dig in and see how.
Okay, so to get to orbiting planets, we've got to start with the basics. And at their core, forces are, well, they're just pushes and pulls. That's it. And the very first thing you'll notice about them is how they can actually change an object's shape.
Right. When you apply a force to something, you can deform it. You can stretch it, you can squash it, you can bend it. Now that might sound super obvious, but think about it. It's the most direct, visible proof we have that some invisible force is at work. I mean, just think about your day-to-day life. Squeezing a sponge, stretching a spring, bending a ruler, or compressing a tennis ball. In every single one of those cases, a simple push or a pull is visibly changing the object's form. It's like the universe is showing its work, letting us see that a force has been applied.
But just seeing this happen isn't quite enough for science. The real question is, can we measure this relationship? Can we actually predict how much something will stretch if we apply a certain amount of force? And it turns out we absolutely can, with a really, really simple experiment.
It's called the load extension experiment. And here's how it works. You take something stretchy, like a spring, and you measure its length. Easy enough. Then you hang a known weight on it, that's what we call a load, and you measure how much longer it got. That difference is the extension. And then you just keep doing it. Add more weight, measure the new extension, and write it all down.
Now, the reason we usually use something like a spring is because it's what's known as an elastic solid. And this is a really important detail. It just means that when you take the weights off, it snaps right back to its original shape. The change was only temporary, which is perfect because it lets us measure a consistent relationship over and over. And when you take all your measurements and plot them on a graph, something really cool happens. A clear pattern pops right out. You see that the more load you add, the more extension you get. In fact, for a lot of materials, for every new chunk of weight you add, you get the exact same extra bit of stretch. It reveals this beautiful, direct, and predictable relationship between force and deformation. Of course, the real world is rarely that simple, right? Usually, objects have more than one force acting on them all at once. To get our heads around that, just picture a game of tug-of-war. It is the perfect analogy for what happens when forces start to compete. So, to figure out who's going to win this tug-of-war, physicists use a concept called the resultant force. It sounds technical, but it's really simple. It's just the overall effect, the single final force that's left over after you've added up all the individual pushes and pulls. It's like the final score of the game. And this whole idea really boils down to two possible outcomes. On one side, you have balanced forces. This is when both teams are pulling with the exact same strength. The resultant force is zero, and that rope isn't going anywhere. But on the other side, you have unbalanced forces. One team pulls just a little bit harder. Now there is a resultant force, and the rope starts moving. This difference between balanced and unbalanced forces, well, it changes everything. Now, that idea of a zero resultant force, of perfect balance, it actually leads us to one of the most mind-blowing ideas in all of science. It's about what things do when you just leave them alone. What is the universe's natural default setting? So let's just ask the question directly. Based on what we saw with that tug-of-war, what do you think happens to any object when all the forces acting on it cancel each other out and the resultant force is zero?
And boom, here's the answer, from Isaac Newton himself. It's one of the most famous lines in all of physics. Basically, an object that's not moving will stay not moving, and an object that is moving will keep moving at the same speed in the same direction unless an unbalanced resultant force comes along and messes with it.
I mean, this is a huge idea. The default setting for everything in the universe is to just keep doing whatever it's already doing. Motion itself doesn't need a force to keep it going. It's a change in motion that requires a force. This built-in resistance to change is called inertia. It's the reason you lurch forward when a bus suddenly stops. Your body is just trying to keep going. So, that brings us to the final piece of our puzzle here. If a resultant force is the only thing that can break through inertia and actually change an object's motion, what does that change look like? What are the two main jobs that a resultant force does? The logic here is pretty straightforward, right?
If no resultant force means no change in motion, then it has to follow that having a resultant force must create a change in motion. There's no other option.
And that change to an object's velocity really comes in two main flavors. A resultant force can change its speed, make it speed up or slow down. Or it can change its direction of motion. Or, of course, it could do both at the same time, like a car turning a corner while hitting the gas.
And really, that's the whole story in a nutshell. A simple push or pull. That's all a resultant force really is. And that simple push or pull is responsible for every single time something speeds up, slows down, or makes a turn. It's what makes the world go.
So let's circle all the way back to our first question. A rubber band stretches because you pull on it. A planet orbits a star because a force, gravity, is constantly pulling it, constantly changing its direction. But if a force is just a push or a pull, what exactly is doing the pulling when it comes to gravity? Now that is a question that takes us even deeper into the incredible rules that run our world.